We can begin now. Pleasure to present part 2 of Marius Dadarlat's Introduction to Continuous Fields of C-star algebras and their topological invariants.
Thank you. Okay, so I will not repeat the definition of continuous fields, right? But for most of the talk, we restrict to nuclear continuous fields. So the continuous field of C-star algebras, right? The C-star algebra of sections, it's a C-star algebra, and this is what I mean. That C-star algebra is nuclear. And then, if that is the case, right, hence by this theorem of Etienne Blanchard and Kirchberg, but in the nuclear case, which was Etienne, say A embeds C of X linearly in C0X tensor 2. Okay, so we just have a sub-C-star algebra of continuous functions from X with values on O2 vanishing at infinity, which is a C of X module, and that's the general case. All right, so, and in particular, right, the map onto fibers, right, is in this picture is induced by evaluations of X. You can evaluate an X fiber wise and then compose, and that's the fiber. So, all right. Now, one of the goals of our study was to extend the Dixmier-Douady theory to a general class of continuous fields of nuclear algebras. Right, so if you ask, if you have a continuous field, if each fiber is nuclear, then the continuous field is nuclear. One just uses partitions of it. Okay, and I'll recall this definition that so let A be a continuous field over a space X, so it's locally compartmentizable space. Right. With all fibers isomorphic to the compact operators. So there are, say, with fiber abstract isomorphic to the compact operator. Okay, and Fell introduced the following condition. It's implicit, it's called the Fell condition. Says that okay, A satisfies the Fell condition. If there is an element P in A, which, when restricted, okay, sorry, it should be for each point. Yeah. Okay. So maybe I'll continue. If for any X in X, there is the neighborhood of X, and there is an element of A such that for any V in V, P of V, right? So what do I mean by P of V, right? It's the image of P in the fiber is a rank 1 projection. All right. And Dixmier-Douady, they studied fields of compacts, and they have several results. And I will emphasize two. So if I have a continuous field over X with phi by K, okay, that A, okay, so now suppose X has finite covering dimension. Then A is locally trivial. So here it's a bundle of compacts if and only if it satisfies the third condition. And they also show by an example that this fails if X is infinite dimensional. Okay, so fails if dimension for the Hilbert cube. All right, and then when restricted to locally trivial fields, they show that those can be classified. So this I will state as a second theorem. And the second theorem says that locally trivial fields of compacts are classified by the third check homology group with efficiency in Z. And it is more to the story. I will introduce this notation CKX, and in general, these are locally trivial continuous fields over X with fiber K. So in the future, I might put some other generic fiber there, D. CDX would be locally trivial fields over X with fiber, the system algebra B. So that isomorphism classes of such fields, so they form a abelian group with respect to operation of tensor product, and in fact it is this group which is isomorphic to H3. And then they have this map called the Dixmier-Douady class. Characteristic class. Okay, so the plan is to discuss various generalizations of these two theorems. And today I will focus on a discussion of the first theorem, how to extend that theorem. All right, so now I already explained in the first talk that really the failed condition should be regarded as a K-theory condition. Okay, so maybe I will give a generalization.
Why 3? What's special about 3? H3?
Sorry, what is special?
About 3, H3. You said it's classified by H3.
Yes.
Where does the number 3 come from?
Yes. So it's the autographies of the compact. This is the infinite the unitary group of the Hilbert space, the circle, and this is what topologists call a KZ2 space. So all homotopy groups are zero, with the exception of the second homotopy group, which is Z. And then bundles are classified by homotopy classes into the classifying space of this. And this then would be a KZ free space. So all the homotopy groups are zero, with the exception of pi 3. And it's just because, so in other words, just because all the homotopy of these groups lies in one dimension, dimension 2, leads that the classification can be done. And then if we go to more general algebras, then the homotopy, we need still a flexible automorphism group for which you can compute homotopy, and then characteristic classes will show up also in other dimensions. And for some algebras, like the universal UHF algebras, we have a precise joint work with Ulrich Pennig generalization of this, where here we have homology with special conditions. All right, so, but that will make the subject of my last talk. So for today, I will focus on local triviality. Okay, and so this would be a generalized condition. Okay, and so D would be a C-star algebra, really a nuclear C-star algebra, and A would be a continuous field over X with fiber all isomorphic to D. Okay, and we say that A satisfies the Fell condition. Okay, so if, all right, so it's a local condition for any x in X, that is V a closed neighborhood of X. And now, you see, this requires K theory, and I will explain, give more explanation in a second. There is an element in KK from D to the restriction of continuous field to D. Such that if I compose with the quotient map into the fiber, okay, for each point, then I get a KK equivalence. For any I will give some more intuition on this, but maybe I'll call this the global Fell condition. Right? If you can choose V to be X, so that means that there is sigma in KK V and A, such that one evaluates each fiber and gets an invertible. All right. So say that maybe A is isomorphic to a continuous function from X with values in a system algebra D, right? Then I have this embedding of D in C of X D. This as embedding as constant function D goes to constant function D, right? And this is abstract, it's isomorphic with the continuous field, right? So by C of X linear map, right? And then I evaluate, I go to the fiber of X, right, which is isomorphic to D, right? And you see, really this condition if you think that this is like some sort of a global section, and then which evaluate in each fiber, you can see that in each fiber gives a map from D to A of X, which modulo this identification is the same thing as identity. Okay, so you should get an invertible map. So now, for people not familiar with KK, you know, it's perfectly okay to think of sigma being induced by star homomorphism, maybe eta from D into A, or maybe A. So you have a star homomorphism, such that when you evaluate to the fiber, then you get a family of star homomorphism, and each of them you want to induce bijections on K theory. More generally, you know, they should be invertible. So if they satisfy the universal coefficient theorem with this fiber, then you check invertibility just by checking that sigma V induces bijections on K0 and K1. All right, and then let's make another node. Right. So if I'm looking at KK of the compact operators and A, you see, I'm looking at the Hell conditions where the fiber B is the compact operators, right? So this, we know by universal coefficient theorem, this is first of all, this is like maybe KK of C and A, and by the universal coefficient theorem, this is homomorphism from K0 of C to K0 of A, right, which is homomorphism from Z into K0 of A, which is isomorphic to K0 of A. Okay, but maybe even before on the other, right. Okay. And if I want to look at K and A or V at a certain point, right, this would be isomorphic to Holmes Z, right? And now, if I'm looking at KK equivalences, this would be bijections, and that happens precisely when those homomorphisms send 1 to plus minus 1. Okay. So then, with this in mind, it's clear that what Fell condition asks is that this generalized Fell condition overlaps almost entirely with the classical Fell condition, except that we ask 1 to descend to 1 rather than negative 1. So really it's the same condition. And of course, it looks simpler. Why? Because K0 of D, which is K0 of the compacts, with Z. But otherwise, the same. And of course, with this in mind, you should have local sections. Of course, if I impose such a condition, it's very strong. But you see, we introduce this generalized Fell condition purely in the language of K theory. So it's a topological condition. Now, in general, if you have a complicated object, you don't expect that the topological condition will imply an analytic condition, which is the local triviality. So that will happen only in exceptional cases. But one of those cases is the class of Kirchberg algebras and the class of UHF algebras of infinite type, and also more generally the class of strongly self-absorbing sister algebras and their stabilizations. Okay. Okay, so we are pursuing that first theorem of Dixmier-Douady, right? But we aim to replace the Fell condition by this generalized Fell condition. So in the previous talk, we constructed a field whose fiber was a Kirchberg algebra, the same Kirchberg algebra, over the unit interval such that that field was not trivial around, locally trivial around any point. Right, so it would be totally singular. And then another example was constructed over the Hilbert cube, where the fiber is the same Kunz algebra U2 or KK contractible. So, and that was also not locally trivial at any time. All right, so let me give this statement, this theorem. Okay, so X would be a finite dimensional compact metrizable space, and D a Kirchberg algebra, Kirchberg system algebra. Right, so this is simple nuclear, maybe separable pyramid. Kunz algebra. All right. And let's say maybe I want for now to D to be stable. Right, so there will be two statements in the case where D is stable, unital or not unital. Okay, if D is not unital, then we know by theorem of Jang it's automatically stable. So, that means that absorbs the compacts. So D is not equal. Okay, let A be a continuous field over X with all fibers abstract isomorphic to D. All right, so right, so then A is locally trivial if and only if it satisfies the condition. And it's trivial if it satisfies the real order. And this is a stronger statement which obviously implies the first statement. So it says that local triviality it's a purely has a purely topological obstruction if the fibers are nice, stable algebraic algebras, and if the space has finite covering dimension. Okay, I want to give you some indication of why this is true. All right, now okay, now I should say that the general case, as stated here, relies on various results of Kirchberg's in continuous field. Now, which involves this parametrized KK theory produced by Kasparov and then also generalized by Kirchberg. However, in the UCT case, there are direct proofs which do not depend on this general theory. So, and those results are also useful to prove this theory. So, let me maybe I'll explain this notion. Right? So, a field, even over the interval, can be having the same fiber peak. Algebraic algebra can be extremely complicated, totally singular. We have seen examples. Now, if one assumes that the fiber satisfies the universal efficiency theorem, there is a decomposition result for such continuous fields. Namely, they can be written as inductive limit of fields which have only finitely many singularities. Okay, so I will describe maybe n pullbacks in a moment. But first, one pullback. Maybe 0, 1. Okay, so what we do is this. So let's say we have an interval 0, 1, and we have a partition into a column partition, 2 columns, let's say. Okay, and on each partition we have a continuous field. So this is a trivial field. Continuous functions, you know, on these intervals with values in D. Now, on the complement, but regarded as union of closed intervals, you might think, you may consider another continuous field, also locally trivial or trivial, but the fibers I can write here D, but what does this mean D? It's something isomorphic to D. And now, I would attempt to glue these two trivial fields together. And the way we do is for each such point, you see this is D, I choose an embedding. This algebra D, embedding in this algebra, in that algebra D. And then the way we define it, so these are as a pullback, I could construct a diagram, but really this is like continuous functions on the unit interval with values in D, such that there is no restrictions on these bold intervals. I have values in D here, but when I evaluate at this point, the value of the function should fall inside the image of this homomorphism. So you see, I'm in D, and here in this middle interval, we fall into subalgebras of D, but which are isomorphic to D. Okay? So that would be a one pullback. In my notes, you glue this just like as you have a cocycle to glue bundles. But the cocycles, these maps gamma I, J, are not automorphisms, they're only injective. So maybe what would be two pullbacks? Okay, two pullbacks to give you an idea. So I think this will be on two-dimensional spaces. So you can imagine like some artistic staircase. There are such things, like Michelangelo staircase. This is D, then in some places you fall to a subalgebra, and then isomorphic to D, and some other places you fall even lower, maybe to another algebra, still isomorphic to D. See, this is a continuous field. All fibers are abstract isomorphic to D, but if you look at the picture, right, it looks like the field is not locally trivial around those edges. Well, that's not clear, right? So what happens, as I explained last time, this field, the condition that this field, one pullback, it's even though it looks like it passes to a subalgebra, it can still be trivial. Locally trivial, and the precise condition is that these gluing maps, which are endomorphism in general, but they should be a one parameter path which starts at that map, and the rest of the way continues through automorphisms. Okay, so you only are allowed to use endomorphisms which are endpoints of paths of automorphisms. And then you use those paths to straighten this up and show that actually this singularity is only apparent, with no essential. All right. So now, if you have this generalized fail condition, right? So that means that you embed D globally in this field, and then you restrict to fibers. You see, and then no matter what you restrict, you get a KK equivalence, right? And then implicitly will force this gluing these maps to be KK equivalences, and in fact, by Kirchberg's theory, you find a path of automorphisms which end up there. So that's really that. Okay, that sounds good, but that applies only if you knew that the field is a pullback with finitely many singularities. So what do you do in general? Okay, so there is a decomposition approximation result, and it is that result which makes use of the assumption that the space is finite dimensional. So people working, classification and other things, they know the flavor of the argument, when you work with these colored partitions, and then you choose, an army of deltas and epsilon, based on the combinatories of the partition and keep the vertical. All right, so. Right, so okay, so this would be maybe an approximation result. So if A is continuous field over X, over dimension X, and each fiber A of X is a UCT Kirchberg algebra. Okay. Then A is an inductive limit of subalgebras AK, where AK are n fullbacks. On this picture, I illustrated a pullback where the fibers are all isomorphic to D, but in general, n pullbacks, you have D1 here, D2, D3. This structure theorem is functional. And in fact, these are nested, it's an increasing sequence of n pullbacks, and n comes from the dimension. Okay, so that explains. All right. So let's give some applications. Right, so all fields over finite dimensional X with fiber O2 tensor K are isomorphic to whether this is, I said compact, but I'll keep compact. Continuous functions. So you see all fields that are trivial. But remember, in my first talk, I discussed how if we replace X by the Hilbert cube, then this fails. All right, and then, well, we don't give the proof, but let's check Fels, So Fels conditions is automatically, satisfied. Why? Because we know that, O2, O2 tensor K, right? It's K contractible. Right, so K of O2, it's 0. Right, so any element here, it's a KK equivalence. So there's nothing to check. So, once again.
Can I ask a question? Sorry.
Marius,
Yes.
when you said it was injective limits, it's not C of X maps.
It's C of X.
It's C of X.
Yeah.
Or these are C of X embeddings.
Right, C of X. And in my paper, I mean, this is what paper theory is called, I only wrote the proof for the case where there was K1 was torsion free of the fiber, because then that was the best result on semi-projectivity of Kirchberg algebras. Kirchberg algebra is semi-projective, so have this non-commutative analog of absolute neighborhood effect. If and only if its case where it's finitely generated, then K1 was torsion free. But then Dominic Enders extended this to all Kirchberg algebras. So then the same argument gives. Otherwise, there is a more complicated approximation. Right, and you see what happens with O2. So this is how the proof for O2 goes. On the interval, that's already complicated. You approximate it by things like that. And this map is an injective map. Okay, but it's a map from O2 to tensor K to O2 tensor K, which is injective. Okay? But then, like Hirschberg-Phillips, right, you use asymptotic unitary homotopy, and you deform that embedding to an automorphism of O2 tensor K. So you eliminate the singularity. So the approximating blocks, this AK are C of 0, 1 with values O2 tensor K. And then you handle them in the dynamic. And then in high dimension it's 1. All right. Now, what about the unital case? Because you also, so in the unital case, you have to adjust the Feld condition, right? So we have sigma, then we look at the global Feld condition, right? With this condition that sigma V is in KK of V and KV inverse, the KK equivalence, and you want sigma to preserve the class of the unit. So this is in case here. Okay. So you have of course you want to keep track of the unit. And then there is a similar result, right? So radial, so then we have also unital case. All right. Now, the unital case, in some sense, it's more interesting than the stable case, as illustrated by the following example. Okay, so again, X dimensional. Okay, and then unital continuous fields over A over X with fibers, all the fibers abstractly isomorphic to ON. This is the Kunz algebra. A local gradient. Moreover, A is trivial. If and only if the unit of A n minus 1 times the unit is 0, Let's order n minus 1 in K0. So again, all right. So all right. So then, of course, I mean this is not a proof, but it's a verification of why. That unit of Hell condition is satisfied. Okay. So let me explain. Let me explain actually the last part. You see, this condition implies that with some work, but not that much work, you know. Well, this is too much, but you see, you find the unitary embedding of ON into this continuous field. I mean, this would follow from Keyword theory, but if I'm looking at KK ONA, right, so this suggests in home K0, K0, and K1, K1, but K1 of OM is 0, so I have the 0 n minus 1, K0, K. Okay, and I might have a kernel here. However, the elements, you know, to decide KK invertibility, you know, I can decide at the level of K theory. Okay, so maybe I'll give the key remark, right? So if theta belongs to home K0 plus fiber K0 of some fiber AB, right? They are all Kunz algebras, so this is home 0 n minus 1, 0 n minus 1. What do I want to know about this? That it is a bijection. But I know that I have a map, you see. I can find this map from z minus 1 to k minus 1, which sends the class of 1 to the class of 1a. And this is defined. Why? Because the order of the unit, the torsion in K0a is the same as, you know, the order of the class of 1 there. I send 1 to 1, so that's a map, right? And if I evaluated the fiber, you know, 1 is sent to 1. So therefore, the only endomorphism of Z mod n minus 1, which sends 1 to, in fact, to a primitive root, is automatically a bijection. So really, the fail condition is hidden in this property that the field is unital. Right? The unit plays the role of a global rank 1 projection from the Dixmier-Douady. Okay, so right, and then you can realize this condition locally by semi-projectivity. So for people familiar with semi-projectivity, I choose an isomorphism from ON to some AX, to some generic fiber, right? It's an isomorphism by assumption. By semi-projectivity, I can leave this map to A of V, or some V, a small neighborhood of the point. Unital homomorphism. then I take its kk class. Okay, that's the element sigma from Faraday. Right, so it shows that right, if you have these K-theory conditions, they are easy to verify if you have the universal coefficient theorem. Because if you know the K-theory of the algebra, because then you can check, simple algebraic effects, and then you derive a local triviality. Now, Kirchberg has a very general theorem. The details of the proof are not published. However, the special case of continuous fields, it's a lot easier to verify them. I verified those for continuous fields. So. For the UCT case, and that result, I did not use these results that are unpublished. No, the results are published, but not the complete proofs. Okay. But for the general case, the non-UCT case, one those were missed. All right. So. If you have two continuous fields over a space, what is the natural notion of homomorphisms of fields? There are star homomorphisms of C-star algebras which preserves the fiber. In other words, an equivalent way, they are C of X linear. Okay, so right, so for C-star algebras AB, of course, we use generalized homomorphisms up to stable homology. That's a late characterization of K of AB. Okay. Now, if you have continuous fields, okay, then you would want to use KK element which in some sense preserve the fibers. So it's like a continuous family of KK elements, parametrized KK elements. So this was introduced for Hausdorff spaces by Kasparov, and then Hilbert generalized it for non-Hausdorff spaces. And of course, I'm not going to enter into this, but right, I'll just say this, that the usual picture for Kasparov, KK of AB, consists of an AB by module and a generalized Fedorov operator which has certain properties. Right? Now for KKX, right, we want everything to happen over X. And the condition is that an elegant way of describing it is this. So FA, C, B, A it's in A, F is a continuous function in X. Right, so you see I have this module structure. I should be able to move F on the other side. So really, right, this is not just a Hilbert module, it's a continuous series of Hilbert modules. Because it's a C of X algebra in the continuous field. So you see, this looks like awfully technical, and it is typical in general, right? Because we don't know how to compute those. That's the problem. But the additional condition is this: C of X linearity. All right, and Kirchberg has this theorem, which let's take a special case. Okay, so A, B are unital separable nuclear algebras with limited spectrum. X. Okay, then we know there are continuous fields over X. Okay, this is Hausdorff. And the fibers are simple. The primitive quotients of A and B are simple C-star algebras. Okay, so then we don't know that these algebras automatically absorb are purely infinite, strongly purely infinite, meaning that they absorb the Kunz algebra of infinity. No, but if we knew that, because we don't know, we take tensor products. So if and only if there is an element alpha in K, X, and B, which is invertible. It's a KKX equivalence. Oh, all right. So these should be regarded as, first place, some sort of rigidity theorem, because that's the proper context. Why is that? It says that if A and B, destabilized one, are homotopy equivalent over C of X, or this is what KKX equivalent means. They are homotopic, fiber-wise, in a very weak way, still coherent, then they must be isomorphic. Okay, so that's a pure rigidity theorem. Why? Because, given examples, how can you verify whether there are such elements? If X was a point in the classical Kirchberg-Phillips, still we cannot verify unless you have the universal coefficient theorem, and then we know that amounts to. For instance, this theorem that about O2 that I stated could not have been derived from this one. Because you might say, okay, let's take B to be C of X tensor O2. And take A to be a continuous field with fiber O2. How do I know that it is KKX compactable? Because that's the condition. So that was not known. Okay, so okay, so I studied this question, and then I have a theorem which it's a helpful answer, but partial answer to these questions, but it's useful as a technical tool. Suppose X is finite dimensional. Okay, right? Okay, and so this is for general nuclear fields. They don't have to be fields of nuclear of Kirchberg algebras. A and B are continuous fields over a space X, and they are nuclear. So then it is invertible if and only if it is pointwise invertible. Now I'm removing, I pass to fibers. Of course, you have to trust me that there is such a map. So this KK equivalence is the sigma is a fiber-wise KK equivalence. And now, this is a lot easier to check, because if you have UCT, you only need that this induces bijection, fiberglass. So, right, this is reminiscent of the following. So if you have a numerical function on a space, it's invertible if and only if does not vanish at any point. Takes invertible values at each point. So this is. And you see, we don't have to assume there is a map in the opposite direction from B to A. So, but of course, and the proof of this relies on the O2 triviality theorem, because one takes the mapping cone of this in a suitable triangularized category, and then the mapping cone has all the fibers KK contractible, and then one applies the triviality result. So then the mapping cone is KKX contractible, so this is a KK. All right, so if one has a map, between fields to check equivalence, then amounts to point was equivalent, but of course, typically we don't have this. So this has been answered only, if X is 0-dimensional. If X is 1-dimensional, it's more complicated. We need to assume that there is no torsion
Any questions or comments for the speaker? Let's thank the speaker again.